Okay. Screen share. Okay, continuation with the previous lecture. Today we have another important topic, which is called the aliasing. Aliasing, or sometimes we say it's overlapping. Of course, in the previous lecture, we have discussed three cases. We said that the first case, when we have oversampling, I mean when the sampling frequency is greater than the Nyquist rate. And we have determined the Nyquist rate by Fs equal to 2F maximum. We said that if the signal contains more than one frequency component, at that time we are going to determine the maximum frequency, and the Nyquist rate will be 2F maximum. And the sampling rate must be greater than or equal to the Nyquist rate in order to what? In order to recover the original signal successfully. Otherwise, the original signal cannot be recovered. Well, so in the second case, we said that we have the case of the critical sampling. I mean, when the sampling frequency of the system is equal to the Nyquist rate. And the third case, when the sampling frequency of the system is less than the Nyquist rate. When the sampling frequency of the system is less than the Nyquist rate, at that time, aliasing will occur, or overlapping when we talk about the frequency response. Now, in the case of overlap, the high frequency information aliases, resembles, or looks like. Okay, so these are the three words. Okay, gives the same meaning. Okay, aliases, resembles, or looks like. Low frequency. This effect is demonstrated below. I'm going to show you the next slide. With a high frequency sine wave that is sampled too slowly, even though the sine wave is sampled at regular interval, the reconstruction process fails to reproduce the original signal since the samples are spaced too far apart in time.
Of course, we have to keep in our mind another thing, that the distance between the samples in time, okay, in time must be what? Must be minimized. Minimizing the distance between the sample in time with what will increases the distance between them where in the frequency. As you know, we have inverse relation between time and the frequency. It's possible to fit a lower frequency sine wave to those same data points, which is a time domain illustration of how a frequency signal can allaze into looking like a lower frequency. Well, now we have discussed this case. Now look at the following case. Look, this is the what? This is the case of overlapping, okay, or aliasing. Now, what will be the problem here? Again, in the previous lecture, we talked about what? About the signal reconstruction. Now, how we are going to reconstruct a signal or a sampled signal? Of course, using a low-pass filter. Always keep in your mind something. The cutoff frequency of the reconstructed low-pass filter will be fixed at sampling rate of the system divided by 2. I mean the sampling frequency divided by 2. Now, what will happen if you are going to sample the signal below the Nyquist rate? When you are going to draw the spectrum of the sampled signal, at that time overlapping will occur between the replicas of the signal. So by now, for example, for simplicity, I'm going to talk about, say we are going to use a low-pass filter, then the low-pass filter will passes the required signal plus some leaking energy from the neighbor replica. So this will lead to what? Leads to unsuccessful reconstruction of the signal. Now, again, aliasing may be illustrated as what? As a person who have more than one name. Now I'm going to illustrate what do you mean by the person who have more than one name. Look, please. Here we have in this graph. Can you see the graph? Are you seeing the graph?
Yeah, we
Yes,
do.
yes,
Yes.
teacher.
Yeah. Okay. Now, um, well, now here we have points. Look at the points. Point number 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay. Now here we have what? Here we have points. Now, the bold sine wave. Look at the bold sine wave, please. It passes through what? Through these points. Okay. Then we have another sine wave which is higher in frequency than the bold one. Again, will passes through the same point. Really, we may what? We may pass infinite number of sine waves through these points. Okay. So the question is now you have what? You have two sine signals. Well, now we have two sine signals. Bold one and the high frequency one, or low frequency and high frequency. Now, when someone asking you about these points, now these points belongs to the sinusoidal signal of low frequency or belongs to the sinusoidal signal of high frequency? Of course, you don't have the ability to say that these points belongs to the two sinusoidal signals. Okay, we have to have what? We have to have a unique function that will describe these points. Now my question is, these points belongs to the high frequency or to the low frequency in your opinion?
I think it's from high frequency.
It's good. You think that's from the high frequency?
Yeah.
Another answer? or another opinion? Now, really, we have more than, I said, this is a simple example. I am passing two sinusoidal signals through these points. Practically, we may pass infinite number of sinusoidal signals through these points. Okay, so this is called ambiguity or ambiguous. Okay, so this confusing. Okay, or fuzzy. So we have to what? We have to have a single signal. So how these two signals may be at the input of the system. So if you are going to proceed the input of the system by a low pass filter, at that time high frequency signals will be what? Will be removed, and only the what? Only the baseband signals or the information signals will be passed to the whom? To the system of the DSP. So in the previous lectures, when you talk about the basic diagram of the DSP system, we said that at the beginning we have a low pass filter. Really, this low pass filter is called what? It's called low pass filter, yes, but it's an anti-aliasing filter. Okay, this will be the anti-aliasing filter. Next week, inshallah, we may have some numerical examples about the aliasing. The next week, I'm going to talk with you about some numerical examples of aliasing. I'm going to solve examples to show you how we are going to make use of the aliasing phenomena. Okay, now let's go to another lecture. بله
بس بري في بحث distance between sampling أنا ما فهمت إيش تقصد بيها.
شنو؟
أو point من حكيت عن المسافة بين السامبل.
إيه.
هاي ما فهمتها.
دقيقة واحدة. بس دقيقة. إيه. بس أعطوني دقيقة واحدة أستفهم شو المقصود. Okay. Okay. Well. It's okay. Well, now you see the whiteboard, okay? Are you with
Yes,
me?
we do.
Yeah. Okay.
Yes.
Now let us talk about the sampling instance and what do you mean by the minimizing or increasing the distance between the samples. Let us talk about this signal. Okay, this is an analog signal. Now I'm going to take samples from this signal. Okay, so this will be, say, first sample, second sample, third, fourth, and so on. Okay. Now, what do you mean by distance between the samples? This is the distance between the samples, and this will be the sampling instance TS. Of course, whenever you are going to increase TS, increasing TS means what? Means you are collecting less number of samples. Okay. To understand it more and more, okay, say that we have a 1 second. Okay, 1 second. I'm going to collect information from the signal for 1 second only. Well, now assume that that the sampling rate TS equals to 1 millisecond. Okay, now if the sampling rate is equal to 1 millisecond, I'm talking in time. Now, how many samples we have in 1 second? How many samples we have? It's very easy. Number of samples.
1,000.
Huh?
1,000 samples.
1,000. Yes. Number of samples will be 1 second divided by 1 millisecond. Okay. So in this time, for this case, I have what? I have collected 1,000 samples for what? For the 1 second. Well, now what will happen if we are going to reduce the sampling instance? Okay, to reduce the sampling, say I'm going to select, for example, TS equals to 0.2 second. Okay, so in this time, I'm going to what? I'm going to select only 5 samples. Okay, of course, in the second case, when we are going to minimize or reduce the sampling instance, this will lead to what? Will lead to bad sampling rate or unsuccessful signal reconstruction. Again, I'm going to explain another thing. For example, now when someone asks you to draw a curve, okay, to draw or sketch a curve, how many points you need to sketch a curve? Oh, it's good. This is a good answer. Okay, how many? As much as we could. We need points. Okay, to collect and to what? To draw an accurate graph. Okay, the same story here. We are looking for what? We are looking for collecting large number of samples, of course, as possible as we could. Okay, of course we have limitations. The limitations are due to what? Are due to the bandwidth of the A to D converter used. Well, so this is the restriction. So our aim to minimize the TS as much as possible. Okay, this will be about the sampling instance of the signal. Okay, now let us go to the another topic, which is the quantization and the quantization error. I'm going to illustrate these things. Slide share again. Now you can see the slides for the lecture number 4. Lecture number 4 will deals with the quantization in detail. Of course, by now I'm going to talk about the quantization, and I'm going to explain the effects of increasing and minimizing the number of bits on the system performance. As you know, whenever we are going to deal with any signal using the DSP techniques, first of all, we have to sample the signal. We said that after sampling the signal, the output signal is called what is called discrete time signal. Discrete time signal. Why it is called discrete time signal? The x-axis or the time axis, okay, T axis. At the beginning, we have what? We have infinite number of values on the T. After sampling, the signal only is defined at discrete points. 0, TS, 2TS, 3TS, 4TS, and so on. Well, so this will be after what? After the sampling. So let me talk about this important point. After sampling, the continuous time signal becomes what? Becomes discrete in time. The x-axis becomes in term of what? In term of t S and its multiples. Well, in the second stage of the sampling, say, we have an important operation which is called quantization. Quantization, or what? Or approximation. Quantization or approximation. Now I will show you something to illustrate what I'm talking about. Let's make that قبلنا. Yes. Nice share. Now, to understand what I'm talking about, look please. This is the time axis. This will be T, and this will be V. V of T, okay? V of T or I of T. V of T and T. Now, we said that after sampling, what's going on? Look, please. Say here we have this signal, and using the sampling, okay, well, red lines represents what? Represents the samples of the what? Of the signal, of the discrete time signal. Look, this will be 0, TS, 2TS, 3TS, 4TS, and so on. Okay. Now, look, please. The T axis, okay, the T axis becomes what? Now, NTS, okay, NTS. And N is what? Is an integer number. Well, now, what does it mean? It means that between 0 and TS, we don't have a signal defined between 0 and TS. Between TS and 2TS, again, we don't have a signal. Between 2TS and 3TS, again, we don't have signals, okay? So the signals only available where? At NTS, okay? What does it mean? It means that the continuous axis becomes what? Becomes discrete axis, and only it has the following values. I mean 0, TS, 1 TS, and 2, say, for example, infinity. Now, quantization, due to the quantization, what we are going to do, again, we are going to find out new levels. This new levels is called what? Is called Q or delta V, okay? Now, due to the quantization, we have a variable called delta V. Delta V represents V full scale divided by 2 to B, where B represents number of bits used in the A to D converter. Now, keep you in your mind, I'm going to what? I'm going to convert the T axis to the discrete axis. This is due to what? I mean, T becomes NTS due to what? Due to sampling, okay? And the y-axis or V of T axis becomes again a discrete axis due to what? Due to quantization. Well, so due to quantization, the y-axis becomes what? Becomes a discrete axis. Now let's go back to the PowerPoint slides. Well, sampling and quantization are necessary prerequisites for any digital signal processing operation on analog signals. A sampler and the quantizer are shown in the figure below. The hold capacitor, I have talked about the holding capacitor to hold the samples for each measured sample x of n t for at most t seconds, during which time the A to D converter must convert it to a quantized sample. course, now we have something called real-time application. As I think you have heard about real-time applications, okay? Now, in the A to D converter, we have, it is a real-time application. How? I said many times, any instrument, any device, anyone has what? Has a response time. For example, when we are going to put the sample value at the input of the ADC converter, it will take some time to convert, okay, to convert the sample into its equivalent bits or digits. Well, this time is called what? Is called conversion time. Please, I'm going to repeat this important information. When we are going to put at the input of the ADC converter a sample, to convert this sample into its equivalent digital bits, this process needs time. This time is called conversion time. Well, this is an important thing. Now, as we have talked about the TS and the distance between the samples, well, now say that TS is equal to, for simplicity, I'm going to talk about it, okay? Say that TS is 1 second, okay? We don't have such a sampling rate, okay? Say that TS is 1 second. Well, I mean at T equal to 1 second, I'm going to take first sample. At T equal to 2 seconds, I'm going to take the second sample, and so on. Well, now the conversion time of the ADC converter must be less than 1 second, okay? Why? Do you know why or not? Hmm? Can anyone answer this question? We
Can you
said
repeat
that.
it, please?
I'm going to repeat it. Okay. Well, now we said that any ADC converter needs what? Needs time to convert the sample to its equivalent digital bits. Well, this time is called conversion time. Now, I have assumed a new thing. We said that, say we have sampled a signal by sampling instance TS equal to 1 second. 1 second. Now, the conversion time of the ADC must be less than 1 second. My question is, why it must be less than 1 second? What will happen if the ADC conversion time is greater than 1 second?
Say the sample at تيودويد نو در كابتن
ايه
يعني sample تنشو ورقيري تو محتاج وقتي دوكو convert كتن ورأسا دا تو اس رأسا sample دي ورقيرتن
بالضبط. يعني in other words what will happen يعني تشتكي دي تشيبو نا مشكلة دي تشيبو نا مشكلة تشتشتا
sample نو ورقيرت سيدو
أظن نا أنا شيء overflow يعني نا
بلا سيدو
overflow يعني أو نجي هنا أو تحويل كده رأسا إيه قاد جهات نا
بلا سيدو
okay, so it's what is it's an overflow case. So to be real-time application, the conversion time must be less than TS. Okay, what does it mean? It means that the requirement for what? The requirement for high-speed ADC converter. Of course, high-speed ADC converters means what? Means working with high bandwidth, and it will cost too much. Okay, now X quantize of NT, which is the representable by finite number of bits, say B bits. The B bit word is shipped over the digital signal processor. Now this is the diagram for the sampler and the quantizer, sample hold circuit and AD converter. Now, after digital processing, the resulting B bits word is applied to what? To a D to A converter. Okay. Now we have the reverse process, which will converting the digital bits into analog signal again, which converts it back to the analog format, generating a staircase output. In practice, the sample and hold circuit and ADC may be separate models or may reside on board the same chip. The quantized sample XQ of NTS being represented by B bits can take only one of the 2 to power B possible values. Another digital converter is characterized by full scale range R. Of course, keep in your mind, when we are talking about a system with single VCC, at that time, the full scale range R equals to the VCC, okay? If we are working with another system, say it has 2 VCC, I mean plus VCC and minus VCC at that time, V full scale range will be 2 VCC. Well, voltage swing between minus and a plus, which is divided equally for uniform quantizer into 2 to power B quantization level, as shown in figure below. The spacing between levels, called the quantization width or quantization resolution, is given by Q equal to R over 2 to power B. Sometimes it's called Q, or in other textbooks uses delta V. Look please at this graph. This is a very important graph. Look please. Now, here we have R over 2 and minus R over 2. Of course, R over 2 and minus R over 2, it may be replaced by VCC, and this will be the minus VCC in real. Now look, here we have 0, Q, 2Q, 3Q, and so on, okay? Minus Q, minus 3Q, minus 2Q, and minus 3Q, and minus R over 2 level. Now look, please. This will be the staircase of the D to A converter. Okay, now look at this signal. The line, especially I'm talking about this point, okay? As I think you see the mouse pointed to where, okay? I'm going to take this sample. Look, please. Now, taking this sample at this point, now this sample doesn't lie where on the 2Q or the 3Q level. So what we are going to do, we are going to approximate this sample value to the nearest quantization level, okay? To the nearest quantization level. Of course, we are going to what? We are going to approximate this point to the what? To the 2Q. Why? We said that to the nearest quantization level. I mean, look the distance from the sample value to the 2Q and measure the distance between the sample value and the 3Q. Which distance is less? It's very clear that the distance to the 2Q is less, so the sample value will be approximated to the level of 2Q. Okay, now what does it mean? It means that we have what? We have approximated, we have rounded the sample value to the what? To the nearest quantization level. بله هيك
يعني إذا كان عندنا يكون بالنص، يعني مو إنه قريب جفي أو نجفي ابني فيدا يعني.
أنا نزك بله خب ده مثلا أب نقطة نزك أبو كي بو 2 كيو يا بو 3 كيو نزك ترى بو 2 كيو.
سيدا أزفيتي جاش بس هجا ابني بكيدا.
يعني
متساوي.
يعني سيدا قصدي هجا 2.5.
دقيقة أجر يعني أجر فيري مثلا أب نقطة النيفي مثلا نا okay, it will be, say for example, if it's lie in the midway, okay, in the midway يعني ما بين 2Q و 3Q نا
بله
أجر ما بين 2Q and 3Q exactly, it will be approximated to 3Q, to the higher. It's okay?
Yes, sir.
Well, avail. Well, now you understand what I mean by the quantization. Now, what do you mean by quantization? So, which one? Anyone can explain what do you mean by quantization? شيء quantization يعني شو تشتغل؟ Huh? Can anyone tell me what do you mean by the quantization?
The amplitude وما discrete.
شاو؟
اللي يعني توضيح كرنا السيجنالوميا
توضيح؟
quantization.
لا توضيح.
بله.
يعني مقصدك ايش تشتغل عن توضيح؟
يعني سيدا يعني وكي ولك امشين بدرت عامل قال سيجنال اخو بكن ايش وكي وقت اللي حوالي ساينوسويد دابت.
يعني بس quantization بالضبط شو تشتغل يعني؟ اجا مثلا بتبين مثلا بمرورك مثلا تبي مثلا فلان تشتغل quantization. براستيشيا تقريبا اوكي approximation rounding اوكي rounding لو بس بري خبدن من هاي اكتشتمن يا هاي بري خبدن due to the quantization or due to the rounding or approximation what will happen بس بري خبدن رجاء actual value افيا طبعا actual value نوكا quantization value چنده او شو بو level number 2q يعني ما تشتهي ما هي error هي نافيني شيء نافيني actual sample and quantized sample. Well, we have what? We have error. This error is called what? It's called a quantization error. Of course, this error is generated due to what? Due to the approximation. Approximating the sample value to the nearest quantization level. This will lead to what? This will lead to error. This kind of error is called quantization error. Okay, now typical values of R in practice are between 1 and 10 volts. يعني ما تشتى VCC يعني انه مثلا تهي any electronic devices, okay? Electronic devices say radios, say mobile unit, say any electronic devices we have, the batteries or the supplies for these instruments will ranges between 1 and 10 volts. Okay, so 1 to 10 volts, this represents what? Represents the R or the full scale range of the signal. Figure on the previous slide shows the case of B equal to 3. Okay, here in the previous slide or this slide we have discussed B equal to 3. When we talk about B equal to 3, it means that what? We have 2 to power 3, it means 8 levels. No? 1, 2, 3, 4, 5, 6, 7, 8 levels. Well, so we have 8 levels and assumes a bipolar ADC converter, which is possible quantized values lie within the symmetric range minus R over 2 to R over 2. Of course, what do you mean by unipolar and bipolar? What do you mean by bipolar?
يعني سيدا متعدد الاتجاهات.
عافية متعدد يعني نوكا شيء متعدد يعني نوكا بلس
انا لوك تو ديجيتال انا لوك.
لا بايبولر بس بدي خب نوكا عاد فيري بايبولر يعني موجب وسالب بلس وماينس
انا بجتدي تمام.
اري تشنجو بري خب ده افا ما هي بلس وهي ماينس افا ار اوفر 2 and minus ار اوفر 2 افا شو تشتا افا بايبولر مثلا انا قلت هي مثلا صفر حطها بس موجب افا شي افا يونيبولر او صفر وحطها سالب بس افا جي يونيبولر قلت هي بلس وماينس هردو بيكفن اف سيجنال نافيوي بايبولر. اوكي بايبولر
سيدا
بلي برا
سيدا بس بي تشيا
بي نمبر اوف بيتس
يعني سيدا نوكا بس زحمة بس يعني عاوز تلاقي بيري نوكا
ايه كلامك
سيدا فيرا نمبر اوف بيت ام تشو تعيد يعني مثلا تو بي جيما انت بي ام بزوني
لا افا اكزامبل طبعا بس بشرحيه افا سحكه زانش تشتا سحكه كان ليفل تا هاي البيري تدي شيء تحديد كي نمبر اوف بيتس بري خوب ده كان ليفل تا هاي افا اول ليفل افا دو سي شار حطها هشتنا هش ليفل 2 to power b 2 to power b equals to number of levels اگر تهي 2 to power b equal to هشت بي چنده لوج بيس 2 بو هر دولايا راسا بيدي دركت سه درسته
تمام
يعني تو بيش معناتها كا چند ليفلتا هي بيش تنجي تدي شي حساب كي كابي چنده
درست السيدة.
درسته عزيزي أستاذ شاهد. Okay. Now, in practice, the input signal x of t may be preconditioned by analog means to lie within the full scale range of the quantizer, that is minus r over 2 and r over 2 before it's sent to the sample and the quantizer. As نظام تورقت موضوع عويدي amplifiers أو لا amplifiers هي مثلا كلاس A كلاس B amplifiers اللي تورقت هو صدق
ليش هذا ما ورقت كور الكترونيكي كورسيكي
تظاني طبعا ما هي in electronic circuit analysis ما هي DC analysis و AC analysis ما هي okay. So using DC analysis, we may shift the signal up and down by what? By a circuit called DC level shifter, okay? And by using the DC level shifter, we may force the input signal to lie within the required range of the signal. The upper end, R over 2 of the full scale range, is not realized as one of the levels rather than the maximum level is R over 2 minus Q. راسي أفرو زاينة مدفيد نافيد طلبي بخينم يعني. Are you ready? I'm going to read your names. نافيد وان دا بخينم كاسح كي موجودة كينا موجودة. درست يا جماعة؟
درست.
أول شيء آخينك موجودة؟
بله سيدة.
آلان يونس. آلان يونس. لا موجودة. آية آيات.
بله سيدة.
آواهي.
بله سيدة.
أورفا.
بله سيدة.
أري. آچم شيخ موسى.
بله سيدة.
أسماء.
بله سيدة.
آسيا أحمد. آسيا. عاشور سمير. عاشور. الياس إبراهيم.
بله سيدة.
إيمان إسماعيل.
بله سيدة موجودة.
إيمان إسماعيل.
بله سيدة.
إيمان سليم.
بله سيدة.
أفين حسين.
بله سيدة موجود.
سيدة بس مو بمن عاشور سمير.
نافذة شبو؟
عاشور سمير.
عاشور أنت موجود؟ درسته. عاشور. أوكي. بايس. أبا بايزة يا بايس.
بله سيدة.
نافذة شيء بايز يا بايس.
بايز.
أوكي. بنان محمد. بنان.
بله سيدة. بله سيدة.
بياض.
بله سيدة.
ثامر أكرم.
بله سيدة.
عزيزي. جوان جمعة.
بله.
جهاد ناظم خورشيد. خديجة هاشم. خديجة. خولة مغديد. داود سليمان. داود. دلزان محمد.
بله سيدة.
دلشاد محمد مهدي. دلزان.
بله سيدة.
من نقد.
نعرفت شيء؟
آسيا.
بله نعرفت من خاند. بس موجود نبي.
سيدة.
اوكي. درسته.
بله سيدة.
آسيا أحمد. أري.
بله.
اوكي.
بله.
دلزان موجودة؟
بله سيدة.
دلشاد محمد مهدي. دلشاد. دلفين حسين. دلفين. دلين صمد أحمد. دلين. دنيا فخر الدين.
بلى سيدة.
ايه. ديانا نادر.
نعم أستاذ.
اوكي. دلما صباح.
بلى سيدة.
رابر عز الدين.
بلى سيدة.
عزيزي. روجان صالح.
بلى سيدة.
ريجين رمزي.
بلى سيدة.
اوكي. ريوان نادر شاهين.
بلى دكتور.
زانا سليمان. زانا
الفيرما.
ها
هذا الفيرما.
درست. زيد احمد. زيد موجودة. ايه. زينب لقمان. زينب. اوكي. زينة سمير. زينة سمير. جيان عبد الرحمن. جيان. جيمان مجيد.
بلى سيدة.
موجودة. ايه. سامان حسين.
بلى سيدة.
عزيزي. سدرة يوسف.
بلى سيدة.
سهمي محمد يوسف. سهمي محمد يوسف. سهمي. نعم.
بلى سيدة.
موجودة. ايه درسته. سينار صدقي. سينار. نعم. شارين حسين.
بلى سيدة.
اوكي. شمال حميد احمد. شمال.
بلى سيدة.
عزيزي.
بلى سيدة بلى.
درست. شنيان مصطفى.
بلى.
صباح حسن محمود.
بلى سيدة.
صباح موجودة.
بلى سيدة.
عزيزي. صديق ياسين.
بلى سيدة.
علي أكرم. علي أكرم. علي أكرم. فيان جعفر.
بلى سيدة.
فين بنجين.
بلى.
فرهنج.
بلى سيدة.
كمال ريان.
بلى.
كافيس سلمان.
بلى سيدة.
لافا عبد الستار.
بلى سيدة موجودة.
محمد أحمد ياسين. محمد أحمد. محمد جمال.
بلى سيدة.
عزيزي. محمد حسين علي.
بلى سيدة.
محمد زيدان جرجيس.
بلى سيدة.
محمد صالح فخري.
بلى سيدة.
محمد نزار إبراهيم. محمد نزار. مسعود رمضان. مسعود.
بلى سيدة.
عزيزي مسعود. مصطفى جمال. مصطفى جمال. ميديا عبد الغفار. ميديا.
بلى. بلى.
ميديا قاسم. ميديا قاسم. مير أبو بكر. مير أبو بكر.
والله دكتور والله.
عزيزي برا. نبز قاسم. نبز.
بلى دكتور.
عزيزي نبز.
بلى.
نهلة عثمان موجودة. نهلة.
صافي دكتور.
نهلة. نهلة عثمان. درست برا. نكريت حفظت عفو. نهلة موجودة.
عفوا السيدة. بس عفوا السيدة.
بلى كرامك.
تانا بمكت بس زان كم نها تاتا.
تنا بتشيا.
زينب لقمان.
زينب لقمان. بس يقدر قبل الله.
بلى السيدة.
زينب. زينب لقمان. درسته.
دكتور نظام مجيد. دلين صمت.
كيف؟
دلين صمت.
دلين. لا دقيقة والله.
بلى.
دلين صمد. دلين صمد جي موجودة. وكرامك.
دكتور العفو. نوبة مش نوت يا.
نعمتك شيء.
داود.
داود. كاي دقة. داود سليمان اري
إيه كان دكتور موجنا بيا
سيدة
بله
سيدة نوفت حرف ها نوفيني
ناود كي
نوفت
حرف هاء وياء حرف هاء وياء
حطها بورا
مون سيدة
دقيقة هيش تمام اري نواف حج الياس هاي بورا اري نواف او انا موجودة نور حسين نور حسن عفوا نور حسن نور
بلى سيدة
درسته نورة صالح
بله دكتور
نيروش
دكتور
بلى
بس العفو انت ريتنا ضعيف انا شو نوبي بيجم
ها ايه بلا انا مشكلة بس طبعا شيء بس قاعد احكي يعني
عليا كلام سيدة
ايه بلا هابيل يوسف هابيل
دكتور
عزيزي هشام رمضان
بلى دكتور
هلبين علي
بلى دكتور
هنر فرهاد
بلى سيدة
هيلين حسيب
بلى
هيلين موجودة
بلى سيدة
هيلين عامر
بله
وفاء صالح
بلى
يسرى إبراهيم
بله
يعقوب إبراهيم
بله سيدة
إبراهيم
سيدة
بله
بله سيدة بله
إيه
بشم سيدة سينار صدقي جيت هذا بس أنا زمان بشتي ماي كمان درسني إيفانو بيت
كي
سينار صدقي
سي
بس
أبي
هلا بمنو نارتي بشتي ماي كمان إيفانو بيت
إيه بلا
سيدة يانجي هو ما يقدر يروح
إيه ويوسف مطلب يوسف
بله دكتور
عزيزي ويونس نصرت
بلى سيدة
عزيزي بله كلامك
مايكي جنا عبد الله نوفا بيت أوجي موجودة بس مايكي يخرب وياه
كي
ديان عبد الله
فيان
عبد الرحمن سيدة
عبد الرحمن بس يقدر قبل الله بس يقدر
جيان
كي أنا بيبي
ديان عبد الرحمن
فيان
جيان
هذه جيان عبد الرحمن عبو ايه درسته اوكي لك خلاص درسته
دكتور
بلي برا كلامك
دكتور عفو بس أبا أولانو علي الدفمن وارد وانت ريتني نفيجا أكيد فيش ديال داوغن أبا الدفمن
باشي دكتور
اهلا برا
خود دكتور خط قالك ضعيف عندي اس دي مي نوفا بتمام موبايلنا بس ده ساعت كاينه
اها ايه تنافت شيء الان
الان يونس
ايه درسته برا درسته
ودكتور اجي علي اكرم
وكي تنافت شيء
علي اكرم
والان يونس
بس اقدر قبل الله خير اخو حلي
بلى
ايه علي اكرم ايه درسته درسته
والان يونس تشكر سيدا
علي ما شكرت الان يونس محمد سليم علي سرچاوا يا رستك بيجي 10 دقيقه وان شاء الله مجالك هذه دي ان شاء الله عايز سرچاوا خيراتك